Welcome all. Today's topic is two-stage direct couple amplifier circuit. In the previous lessons, we have learned about RC coupled amplifier and transformer coupled amplifier. We have seen the frequency response of these two amplifiers. Now, the third type in the coupled amplifiers. There are three types in the coupled amplifiers. First one is RC coupled, second one is transformer coupled, the third one is direct coupled amplifier circuit. So first see the circuit diagram. If you see in the circuit diagram, we have three transistors with RC collector resistor, and output of first transistor is connected to the input of second, and so on. And with the input Vs and output V0, V output, and with VCC as common and common terminal ground connection. See the introduction. There are many applications in which extremely low frequency signals are to be amplified. In such cases, the coupling devices such as capacitor and transformers cannot be used because the electrical sizes of these components become very large at extremely low frequencies. Under such situations, one stage is directly connected to the next stage without using any coupling devices. This type of coupling is called direct coupling. So why we are going for the direct coupling? Besides, we have RC coupled amplifier which has excellent frequency response in the audio frequency range, and with some disadvantage of less gain and less power. And second one, transformer coupled amplifier, which has excellent matching, impedance matching, and good gain but moderate frequency response curve. In particular, in some applications where we need low frequency, that is less than 10 Hz signals, almost DC signals, which have to be amplified. In such particular cases, see the coupling devices, capacitors and transformers we have used in the last two circuit diagrams. Their physical sizes, electrical sizes of these components become very large. If you see the formula for the capacitor with its physical dimensions, C is equal to epsilon A by W, right? In such equations, if you substitute the frequencies, low frequencies, right, the capacitance size will become very enormous, means very large, and the same will apply to the transformer also. So in order to avoid such bulky and expensive manufacturing of these components, we will go for the direct coupling. In direct coupling, we use simple wires connections instead of capacitors and transformers. Directly one stage is connected to the next stage. Circuit details. The figure shows the circuit diagram of a three-stage direct coupled amplifier using complementary transistors. See, this is a three transistor amplifiers, and if you see Q1, Q2 and Q3, their connections somewhat differ, right? In the Q2, the output is taken across the RC, which is given to the input of Q3, and if you see using the complementary transistors, but here in the circuit diagram there is some mistake, because Q1 is NPN, and I'm sorry, there is no mistake, because in the Q2 the RC is connected at collector terminal, which is a PNP transistor. you reverse it upside down that Q2 transistor, you will realize it. First one is NPN and second one is PNP and third one is again NPN. The first stage uses NPN transistors and second stage uses PNP transistors and so on. So the collector of one stage is directly connected to the base of next stage. The collector of the last stage is directly connected to the load. The collector of Q3 is directly connected to the load resistor. Why we should use complementary transistors? Because the use of complementary transistors makes the circuit stable with respect to the temperature changes. Please make this point. Note, the use of complementary transistors makes the circuit stable with respect to the temperature changes. In this connection, NPN is followed by PNP. The direction of collector current increases when the temperature rises and is opposite for the two transistors. In NPN, the temperature rises because of some internal action. The collector current increases. In case of PNP, it will reverse. That means the collector current will decrease. So when temperature change occurs in this complementary transistors, one output of collector current in one stage, that is NPN increases and PNP decreases. They will balance, they will cancel each other, so the circuit will remain stable. Thus the variation in one transistor tends to cancel that in another. We know with the temperature changes, the IC naught, reverse saturation current, IC naught will double for every 10 degrees centigrade. If you can remember the basic diode properties, the reverse saturation current will double for every 10 degrees centigrade rise. And we know IC is equal to beta IB plus IE. IC is equal to beta IB plus IE. So in that equation, the reverse saturation current doubles and overall the IC will increase with the temperature increase. If you see the frequency response curve of this particular direct couple 3-stage amplifier, see there is no lower cutoff frequency because the frequency range is very small. The low frequencies, this particular direct coupled amplifier we are using for low frequency applications, so there is no low frequency cutoff for this, and there is a upper limit, obviously f2. Then what is the bandwidth? f2 minus 0, that is f2 itself is the bandwidth of this particular direct coupled amplifier. The weak signal is applied working. If you see the working, the weak signal is applied to the base of the first stage transistor Q1. Due to the transistor action, the amplified signal appears across the collector resistor RC of Q1. This amplified signal drives the base of the second stage transistor Q2 for further amplification and is available at its RC. In this way, a direct coupled amplifier raises the strength of weak signal. If you see the circuit diagram, you can easily tell what is going on in this circuit and how the connections are made. First, the VS signal, input supply signal, which is to be amplified, is applied to the base of Q1. Because of transistor action and amplification, the amplified signal will be available at RC. And for the second transistor Q2, the input signal from the first stage RC is given to the base, and at collector of Q2, that is RC2, if you can write, it is RC1, RC2 and RC3, it will be easy for you to explain. So the Q2, because of transistor action, again Q2's output is available at RC2, which is given to the input of Q3. Again, because of transistor action, input of Q3 is amplified and is available at RC3, and final output is at RC3, which is taken as final output of this particular amplifier. Now the frequency response curve of a direct couple amplifier is flat up to an upper cutoff frequency F2. After this cutoff frequency, stray wiring capacitances and internal transistor capacitances play their role. As a result, the gain falls. See, these are important terms. Above the F2, after the F2 frequency, cutoff frequency, stray wiring capacitances and internal transistor capacitances, they will come into action. They will show their effect. Because of those capacitive effects, the output, that is B output, will decrease. So because of that, the gain will also decrease. So what are the advantages, disadvantages and applications of this particular direct couple stage 3-stage amplifier? Advantage: the circuit arrangement is very simple. As you can see, there are lesser number of resistors, there are no capacitors and no transformers, so they are easy and very simple. It uses minimum number of components. It is quite inexpensive, obviously, because there are no transformers, capacitors, which are costly generally. It has the outstanding ability to amplify direct current and low frequency signals. So ability to amplify direct current DC less than 10 Hz literally equals to a direct current, right? And low frequency signals. It has no coupling or bypass capacitors to cause a drop in gain at low frequencies. See, this is the most important point here, because in the CE, if you use the CE, that is emitter bypass capacitor, you can remember across the RE emitter resistance, if we connect a bypass capacitor, that will be causing the low frequency cutoff. But in this particular circuit, we don't use any of those bypass capacitors, so which cannot result in low frequency cutoff. Disadvantage: it cannot amplify high frequency signals, obviously. Particularly we design this particular circuit for low frequency signals. Poor temperature stability, due to the fact that any variation in base current in one stage is amplified in the following stage, thereby shifting the Q point. Temperature stability, though we use the complementary transistors, but the temperature stability is limited. So it is due to the fact that any variation in base current, input base current, due to temperature changes in one stage. So if there is increase in base current due to temperature state, it will be amplified version of the base current. It will be available at IC, that is output current, thereby shifting the Q point, that is stability point. Application: this type of coupling schemes are used for extremely low frequency signals such as photoelectric current and thermocouple current. So these are the typical applications of this direct couple amplifier. Now compare the three available coupling amplifiers, multi-stage amplifiers. Those are first RC coupling, then transformer coupling, and then again direct coupling. First is size and weight. RC coupling size is small, but if you use the transformer coupling, it is large and bulky. And in case of direct coupling, we don't use any transformer and capacitor, so it will be very, very small compared to these two. And cost is less for RC coupling, and transformer coupling it is more, and direct coupling it is the least of these three. And the impedance matching, for RC coupling it is not good, and for transformer coupling it is excellent, and direct coupling it is good. And frequency response is, obviously RC coupling has an excellent frequency response in the audio frequency range, right? We have seen it is between 50 Hz to 20 kHz, and for transformer coupling it is poor. direct coupling, it is at best because we designed for it in low frequency. So in that particular frequency it has excellent frequency response. But if we consider the frequency response of a direct couple amplifier for a high frequency range, it is worst because we didn't design it for high frequency. So whatever the frequency we selected for its application, it's working in that particular range excellently. So that's why frequency response for direct coupling, it is at best, and used for voltage amplification, and for transformer it is for power amplification and for amplifying extremely low frequencies. Right, now we are moving on to the next topic, that is Darlington pair circuit. Darlington pair circuit. If you see the circuit, particularly the 2.14a and 2.14b, first transistor Q1, Q1's collector is connected to the base of Q2, right? And the Q1 again in the B also, Q1's collector is connected to the Q2's. Sorry, if you can see the Q1's, what is that? That is the emitter. Q1's emitter is connected to the Q2's base, and in the second circuit also Q1's emitter is connected to the Q2's base, and the collectors, both the collectors are joined, right? Both the collectors are joined, and both the emitters here represented as a single emitter, and it is a single base. Sometimes the current gain and input impedance of an emitter follower are insufficient. Emitter follower is nothing but a common collector, CC configuration. Emitter follower is a CC configuration. Sometimes the current gain and input impedance of an emitter follower are insufficient to meet the requirement. In order to increase the overall values of circuit current gain and input impedance, two transistors are connected in series in CC configuration. To increase the overall values of circuit current gain and input impedance, so two transistors are connected in series in CC configuration. Such a circuit is called Darlington pair. So this particular type of connection where two transistors are connected in series in CC configuration, this is called Darlington pair. The Darlington transistor acts like a single transistor that has high current gain and high input impedance. That's why it's represented as a single transistor. See the dotted lines, we have only 3 terminals. There are 2 transistors but 3 terminals, base, collector and emitter. So this Darlington transistor we call it as a Darlington transistor itself, since there are 2 transistors but connected in CC configuration, that is acts as the Darlington pair. Acts like a single transistor that has high current gain and high input impedance. The Darlington pairs shown in figure are called NPN Darlington pair and PNP Darlington pair respectively. The Darlington pairs are called NPN and PNP Darlington pair. You know, from the transistor terminals we can identify it as a PNP and NPN. Note that emitter of first transistor is connected to the base of the second transistor, and the collector terminals of the 2 transistors are connected together. We have already discussed that. The result is that emitter current of the first transistor is the base current of the second transistor. See, the result is that emitter current of the first transistor is the base current of the second transistor, obviously, because emitter is connected to the base of the second. Q1's emitter is connected to the base of Q2. See the connection. Right. Q1's emitter is connected to Q2 base. Here also in the second figure also same. So therefore the current gain of the pair is equal to the product of individual current gains. Therefore the current gain of the pair is equal to the product of individual current gains, that is beta is equal to beta 1 into beta 2. It can be shown that the voltage gain of the Darlington pair is less than unit T. Now the amplifier has a reasonable high input impedance of about 500 kilo ohms. The particular single CC configuration, right? We have single CC configuration has a high input impedance of about 500 kilo. If that is also not sufficient for any particular circuit, we go for Darlington pair, that is as 2 mega ohm. Input impedance of Darlington pair is as 2 mega ohm. A formula for the current gain of Darlington pair, right? The current gain of a Darlington pair is equal to the product of individual current gains. Beta is equal to beta 1 into beta 2. Advantages: why we go for the Darlington pair? Because it has some advantage, that is high input impedance, and it has high current gain. It provides low output impedance. It uses very few components. So another advantage are uses very few components and suits well for impedance matching. Impedance matching, because in the input we have high input impedance, but in the output we have low impedance. So this particular case where high impedance signal has to be connected to the low impedance signal, particular this circuit can be used. Disadvantage: major drawback is leakage current for the first transistor is amplified by the second. The leakage current IC0 is amplified by this transistor, and it is given to the input of second transistor. Hence the overall leakage current becomes high. Because of this reason, the cascading of more stages of Darlington connection is not preferred practically. So because of this reason, more number of, we have already seen about 3 stages, but if you want more stages, the leakage current will become a problem. Applications: we can use these Darlington pair at voltage regulators, power amplifiers, high gain operational amplifiers, high current applications. Next is high current gain amplifier using Darlington pair. How beta is equal to beta 1 into beta 2? How that formula is derived? Now see the particular Darlington pair connection with required resistors and capacitors. V input and followed by C1, R1, R2, first transistor Q1 with current gain beta 1, and second transistor Q2 with current gain beta 2, output C2, a particular output V output. And consider the Darlington amplifier circuit where IB1 is base current of Q1 transistor, IE1 is emitter current of Q1 transistor, beta 1 current gain of Q1, IB2 base current of Q2, its value equal to the emitter current of Q1 transistor, right? IB2, see in that we have seen that emitter of Q1 is connected to the base of Q2, so IE1 is equal to IB2, and IE2 is emitter current of Q2 transistor, and beta 2 current gain of Q2 transistor. Now see the derivation. We know that emitter current of Q2 is equal to IE1 is equal to beta IB. IE1 is beta IB, and the emitter current of Q2 transistor IE2 is equal to beta 2 IB2. IE2 is equal to beta 2 IB2, and we know IB2 is equal to IE1. So replace the IB2 with the IE1. So beta into beta 1 IB1, beta 1 beta 2 IB1, IE2 by IB1 is equal to beta 1 beta 2. Let beta be the overall current gain of Darlington pair. So output current by input current IE2, output current IE2 by IB1, IE2 by IB1, that is equal to beta 1 beta 2. So next topic is cascade amplifier. Cascade amplifier configuration using BJTs. See the figure. In the figure we have seen first stage is CE amplifier, it is connected to the CB amplifier. This type of connection is called cascade amplifier, sorry, cascode amplifier. In this case, a common emitter amplifier drives a common base amplifier. Common emitter amplifier drives a common base amplifier. It is well known fact that at high frequencies the gain of the RC coupled amplifier drops. We know from the frequency response curve at higher frequencies gain of RC coupled amplifier drops. This is because of the shunting effect of the Miller capacitance C mu and the emitter base capacitance CE. C mu and CB is because of these capacitances at higher frequencies the gain will decrease. With cascode connections the effect of the Miller capacitance can be seen to get reduced. As a result, the high frequency cutoff gets extended by a factor of about 10. So with this cascode connection the effect of Miller capacitance can be seen to get reduced. See the CE amplifier, we can see the C mu 1 and C mu 2. These are the capacitive effects between the collector and base. C mu 1 for CE amplifier and C mu 2 is for CB amplifier. To make a simplified analysis of this cascode amplifier, assume that the current gain C of transistor T1 is beta and that CB of transistor T2 is alpha. To make the analysis, assume that current gain transistor T1 is beta and CB of transistor T2 is alpha. From basic principles, find that for the C stage, voltage gain AV is equal to beta or output 1 by R input 1, where AV1 is the voltage gain of first and R1 input impedance or output impedance of the C stage. Similarly, we have AV2 is equal to alpha R output 2 by R input 2. So voltage gain is equal to input impedance and output impedance of CS stage. Similarly, we have AV2 is equal to alpha into R0 2 by RI2, where AV2 is the voltage gain, RI2 is the input impedance and R0 is the output impedance of the C stage. From the figure we have find that R02 is equal to RL. Using equations 1 and 2 we get the overall gain of the cascode amplifier as AV is equal to AV1 into AV2, that is equal to beta 1 into R01 by RI1 into alpha 2 RL by RI2. From the figure RI2 is equal to R output 1. Also we have alpha 2 which is nearly equal to 1. Then we get AV is equal to beta 1 RL by RI1. From equation 4 we find that the gain of the cascode amplifier is equal to that of a single stage of the CE amplifier. Even though the cascode amplifier has a gain equal to that of a CE amplifier, we find that its high frequency region of operation extends beyond that of the CE amplifier. This is because, as stated before, the parasitic Miller capacitances C mu 1 and C mu 2 of the two transistors are not directly connected, as can be seen from the figure. See, C mu 1 and C mu 2 are not directly connected. This prevents direct feedback connection between the output and the input of the cascoded amplifier. Next topic is Next is the negative feedback amplifiers. If you see the voltage series feedback amplifier, the feedback signal PF is proportional to the output signal V out. The voltage feedback factor is given by beta is equal to PF by P output. The amplifier in this case is called a true voltage amplifier. The shunt connection. The shunt connection at the output reduces the output resistance or not. The series connection at the input increases the input resistance. In other words, it is obvious from the figure that the feedback circuit shunt the output but in series with the input. So the output resistance decreases because of the parallel connection, parallel combination, whatever it is, while the input resistance is increased, that is series combination, due to the feedback. Next is voltage shunt feedback amplifier. From the figure, the feedback network shunts the output as well as input, hence both the impedance input and output decreases due to feedback. Voltage shunt means voltage sampling and shunt mixing, right? Voltage sampling, in this case we have to take the parallel connection from the output. So the parallel connection means the output impedance will decrease, and in the shunt connection at the mixer circuit, the mixer, if you want to shunt it, we get decrease input impedances. Then the feedback signal IF is proportional to the output signal. V output is given by feedback signal IF by P output. So this type of amplifier is called a transconductance amplifier, because V by I is equal to R, that is impedance or resistance. Opposite of that means the reverse, 1 by R is equal to conductance, right? So V by I is equal to, or I by V is equal to 1 by R. So beta is called the transconductance amplifier. Next is current series feedback amplifier, current sampling and series mixing. It is obvious from the figure that feedback network is in series with the input as well as output, and the input and output impedance increases due to feedback. The trans resistance feedback factor is beta is equal to Vf by I naught. This type of amplifier is called trans resistance because V by I is equal to R. You can remember the Ohm's law, right? So current series feedback amplifier is also called a trans resistance type of amplifier. Current shunt feedback amplifier. The fourth one is current sampling and shunt mixing. For current sampling, you should connect in series with the output resistance, so output resistance will increase. For shunt mixing, you should connect it in parallel. So shunt here, input impedance is in parallel with the shunt connection, so the input impedance decreases. That is stated in the first point, that the feedback network is in series with output and in parallel with input, and the output impedance increased while the input impedance is decreased. The current feedback factor is given by IF by I naught. This is a true current amplifier. Now, nature of various signals in feedback. So types of feedback we have voltage series, voltage shunt, current series and current shunt. The characteristics are output signal. What is the output signal we collect in these types of feedback? In voltage series, we have voltage sampling. So the output signal is connected is voltage. In the voltage shunt, also the output signal collected is voltage. Current series, in the current series, right, the output signal collected is current. And the current shunt, also the output signal collected is current. Now the input signal. Input signal in these types of feedback is for voltage series. In the series mixing, if you can see, if it is connected in series, the voltages in series will add, right? Voltages in parallel, that will give nothing, right? V1 is in parallel with V2, whichever the greater, that will result in the equation. But voltages in series, they will add up. V is equal to V1 plus V2. So in the series mixing, we are actually mixing the input signal in the voltage form. So series means here voltage. And the shunt means I1 and I2 are parallel, then the resultant output I is equal to I1 plus I2. And we don't mix the in signals as series. That means current I1 and I2, if they are in series, there is no resultant I is equal to I1 plus I2. Whichever is greater, I2, that will result. So in the shunt mixing, we are actually mixing the current signal, current form, right? So in series, we have voltage mixing, shunt, current mixing. Current series means series voltage, current shunt means current. Next, feedback signal, XF. Feedback is what is we are connecting at the feedback network, or the output of feedback is, in case of voltage series, it is the voltage. It depends on the series or shunt, we are getting the FZ. That is same as input signal, we get the feedback signal XF. Okay, so we series means voltage, here also voltage. Shunt means current, here also current. Series means voltage, we get voltage. Shunt means current, we get the current. The feedback signal XF, we are actually supplying it to the input. The input signal and the feedback signals are both the same. Then difference signal. What is the difference signal? That is the same as the input signal, because whatever the input we are supplying, the mixer signal will take it. So the V in is equal to Vs minus Vf, or I in is equal to Is is equal to In minus If. So whatever the input signal, that is the difference signal here. Voltage here, voltage, current, voltage, current, and voltage, current. But the basic amplifier A is equal to output signal by input signal Xi. Output signal for the voltage signal is voltage, and the input signal is voltage. So voltage by voltage, we have voltage gain. For the voltage shunt, we have output signal as voltage and input signal as current. So V by I is equal to, so that is means trans resistance, Rm. Now for the current series, we have output signal is current and the input signal is voltage. I by V, we have 1 by R, that is equal to conductance, trans conductance, Gm. For the current shunt, output is current, input is current, so current by current, we will get current gain. Now the feedback factor, beta, is feedback signal by output signal. Feedback signal by output signal. We get first voltage series. What is the feedback signal voltage by output signal voltage? So Vf by V0, we get voltage ratio. For voltage shunt, we have feedback signal, current, and output signal V output. So I by V, we get conductance. And for current series, third type, output is Vf voltage, and feedback is voltage Vf, and the output is current Vf by I naught, that is resistance. Next, current shunt, we have feedback as current If and output as current, so If by I naught, that is current ratio. Like this we can see different types of signals in this particular feedback amplifiers. Now we need to state the effect of negative feedback on gain. So these are the topics for tomorrow's class. Now just go through the today's lecture itself and see, because the time is less, just the revision of today's class. First we have seen about the two-stage RC couple amplifier, which is used for very low frequency signals amplification. It has particular types of applications. See the circuit diagram: 3-stage, Q1, Q2, Q3. Output is connected to the input of second stage that follows, and we use the complementary because NPN and PNP for the thermal stability. And frequency response, if you see, there is no lower cutoff frequency because the frequency range itself very low, less than 10 Hz. So there is only upper high cutoff frequency, and it has a good frequency response within that particular frequency. So signal is amplified from Q1 to Q2 and then Q2 to Q3. These are direct couple, and frequency response advantages simple because lesser components, less costly, ability to amplify direct current. Even low frequency means direct current less than 10 kHz literally is equal to the direct current. No coupling or bypass capacitor, so drops in gain at low frequency is not happen. Disadvantage: cannot amplify, of course we know. Poor temperature stability. Applications: particular applications: low frequency signals such as electric current, thermocouple current. So applications, different particular applications, and we have seen the different types of couplings and comparison of those coupling amplifiers, coupled amplifiers, size and weight, cost, impedance matching, frequency response on particular use. Next we have gone Darlington pair circuit. It is a it is considered as a single transistor. It has the highest current gain, beta is equal to beta 1 into beta 2, and the impedance is also very high compared to the CC. Emitter follower is also called as common collector configuration. So for particular one emitter follower we have 500 kilo ohms of input impedance, but in case of this Darlington pair it is increased to 2 mega ohms, and it has output less impedance, so it is excellent in impedance matching from high input to low input. So current gain is beta is equal to beta 1 beta 2. Advantage is high input, high current gain, low output, very few components, impedance matching, it's leakage current, and these are the particular disadvantages. And applications: voltage regulators, power amplifiers, and high gain operation amplifiers. So next derivation of those: beta is equal to beta 1 into beta 2. See the particular circuit, and IE1 is equal to beta 1 I1 and IE2. This is the main. IB2 is equal to IE1, that has to be remember. Beta is equal to IB1 IE2. Cascode amplifier. Cascode, if you see, CE followed by CB amplifier, and CME1 CME2 are the inner capacitances, and AV1 AV2 and particular derivation of these formulas. So we have gone to these topics, and if you have any doubts regarding these topics, you can mail me at sureshakul2001@gmail.com, and If you want to do the experiments online, you can go to the virtual labs vlabs.co.in or vlabs.iitkharagpur.net. Go to that website and click on list of experiments. You can see what are the different experiments you can conduct online, right? And if you want other resources for extra knowledge in these topics, you can refer the standard books. And if you want to practice for your competitive exams and interview questions, just google the name electronics device and circuits questions. You can use some of the websites also, circuittheory.com for MCQs and other type of questions. So this is today's topics. Thank you one and all.